Hello everyone, my name is Kai and I'm a PhD candidate in Hong Kong University of Science and Technology. Today I'm glad to share our recent CVPR 2025 paper called EMOVA, Empowering Language Models to See, Hear, and Speak with Vivid Emotions. As the title says, this is a work trying to construct multimodal large language models with end-to-end visual, textual, and speech capabilities simultaneously. In May 2024, OpenAI released the remarkable GPT-4o model. Here, O stands for omni-modality. It is actually an end-to-end model with audio, vision, and text capabilities in real time. It provides a novel interactivity among large language models and human users, but also it kind of gives the multimodal research community a warning that perhaps it is time for us to get rid of the traditional binary modality setting, which means previously we primarily focused only on the interactivity among two modalities, either, for example, vision language or speech language. While the release of GPT-4o model actually motivates us to construct full multimodal models with three modalities in a single and uniform model. As we previously discussed, one of the typical existing works is the vision large language models, which tries to integrate the vision modality into LLMs. So to achieve the functionality of omni-modal models, it needs to rely on external audio toolkits to process audio signals, for example, text-to-speech (TTS) toolkits. So this kind of cascade pipeline, on the one hand, it cannot break the modality barrier, but on the other hand, it is also hard to achieve real-time interactivity. Another line of existing works is the speech large language models, which primarily focus on speech-related capabilities like streaming and duplicate speech processing. So of course, it is primarily focused on speeches, and it is totally without any considerations of the vision capabilities. Okay, so the very first thing to consider before we construct large language models is tokenization, because different from text, which by design are discrete signals, speeches, images, and videos, they are naturally continuous signals, and therefore it provides us two different kinds of technical choices, whether to do discrete tokenization or continuous tokenization. But actually, there is not a golden answer to this question, because both discrete and continuous tokenization have their own advantages and disadvantages. For example, for the discrete tokenization, the good thing is that it can perform unified autoregressive modeling for the understanding and generation for the specific data modality. So that's the good thing. While the bad thing is that when we convert continuous data signals into discrete tokens, there will be an inevitable information lossage during the procedure of the conversion, right? So this is the perspective of discrete tokenization. While for continuous tokenization, the bad thing is that it is actually prioritized understanding part, while it is by design not suitable for generation, specifically not suitable for autoregressive generation, right? So this is the bad thing. While the good thing is that if we perform continuous tokenization for continuous data signals, it can better preserve the information in the data signals, and therefore it is much more suitable for fine-grained data understanding. So as we just said, there is no golden answer to this question, and whether or not you choose discrete or continuous tokenization will actually depend on your priority among the understanding and generation. For EMOVA, we utilize different tokenizations for different modalities. For the vision modality, we believe that vision understanding is way more important than visual generation, especially considering the interactivity among human users and large language models. And therefore, for vision, we utilize the continuous tokenization based on the LAVA architecture. Specifically, given an input image, we will first extract its feature using a VIT model, and then which is then projected into the embedding space of the large language models using a vision projector. So that's the vision part. While for the speech part, we believe that the importance of speech understanding and generations is equally important. So finally, we choose the discrete tokenization for the speech modality, and therefore we can use a unified autoregressive objective for both speech understanding and generation. Moreover, to better align the speech modality with LLMs, we further introduced this design called the semantic-acoustic disentanglement into our discrete speech tokenizer. So intuitively speaking, semantic means what the input speech says. So it is more about the semantic content of the input speeches. Okay, while acoustic actually means how the input speech says the semantic contents. So it is more about the speech style of the input speeches. Okay, so by using this disentanglement design, we hope that the extracted speech token sequences will correlate it more with the semantic content of the input speeches, so that as we will see later, it will facilitate the integration among the speech of the input speeches into the highly semantic embedding space of the large language models. Okay, and to achieve this purpose, we utilize a two-stage training paradigm for our speech tokenizer. The first stage, we specifically train the speech tokenizer, which is responsible for converting the continuous speech signals into this kind of discrete speech token sequences. So each of these speech ID will correspond to a unique embedding in the language model's vocabulary. Okay, so by using the CTC loss, the connectness temporal classification loss, we can make sure the extracted speech token sequences will correlate with the semantic contents of the input speeches more. Okay, so that's the first stage of training. We specifically train the speech tokenizer specifically. Okay, while the second stage, we will train the speech detokenizer, which is responsible for converting the speech token sequences back into the speech waveforms. But besides taking the speech token sequence as input, we will further consider a speech style prototype also as input for the speech detokenizer to flexibly convert the speech styles, the acoustic of the output speech waveforms. Thanks to the disentanglement of semantics and acoustic design, we can flexibly convert the speech styles while maintaining the same semantic content of the speeches by using different speech style prototypes while using the same speech token sequences as input. Okay, so this design will further facilitate the emotional spoken dialogue empowered by language models, as we will see later in the instruction tuning side. Based on the EMOVA architecture, we then empirically demonstrate that the omni-modal test-centric alignment by training with both image test and speech test data has been sufficient for omni-modal alignment. And during this procedure, we have several interesting observations. The first one is that image test and speech unit test data can actually benefit each other. To specifically speaking, we first compare these three variants, including the joint variant. The joint variant actually means we train the model with both image test and speech test data simultaneously, while the VLO and speech variant actually means that we conduct the vision language alignment and speech language alignment separately. by using either the image test data or the speech test data for training. And these three figures actually report the transfer results on different downstream multimodal benchmarks. The left and middle figures report the results of different models on popular vision language benchmarks, while the right figure reports the result on downstream speech test benchmarks. So as we can see, the joint, on the one hand, the joint variant can actually perform better than the pure vision language alignment variants on the vision language benchmarks. Okay, so that's one perspective. And on the same time, at the same time, the joint variant can perform better than the purely speech language aligned variant on the speech language benchmarks. Okay, so it demonstrated that by jointly training with image test and speech test data can have better transferability for downstream multimodal benchmarks. We then investigate the benefit of introducing the semantic-acoustic disentanglement for the omni-modal alignment. To do that, we use another speech tokenizer empowered by the Hubert and the K-means clustering. As we can see in the experimental results here, introducing the semantic-acoustic disentanglement can not only achieve better performance on the downstream speech-language benchmarks, but also have better transferability on downstream vision language benchmarks. Finally, we demonstrate that the sequential alignment is not optimal by conducting only one pair of multimodal alignment at a single time, either vision language alignment first or speech language alignment first. The conclusion remains consistent with both the vision language benchmarks and speech language benchmarks that joint training with both vision language data and speech language data can achieve the best performance. After the omni-modal alignment stage, we further conduct an omni-modal instruction tuning stage to better respond to the user's omni-modal queries. Okay, to do that, we collect a small amount of omni-modal instruction data organized in a chain of modality format, integrating multiple tasks within a single data sample, including automatic speech recognition, ASR, text-to-speech generation, TTS, visual understanding, and conversation. Here we provide a vivid data example to better illustrate the data organization. The first part is the system prompt, which is typically organized in the textual format. The user query is consisting of discretized speech token sequences, as we show here, which might also attach with a corresponding image to form the omni-modal context. Okay, so given this context, the assistant is trained to predict the speech responses, which are usually just also represented in this kind of in this form of discretized speech token sequences. And this will be taken as input to the speech detokenizer to recover the final output speech waveforms. But remember, the speech detokenizer actually requires two inputs, right? Besides this kind of discretized speech token sequences, it also needs a speech style prototype to control the acoustic of the final output speech waveforms, right? To do that, we also train the assistant to predict the suitable response emotion and pitches. And finally, the speech style is actually determined by the speaker, the emotion, and the pitch. Okay, overall we support 2 speakers, 3 pitches, and 4 emotions. After that, we will take the speech style prototypes together with the output speech token sequences as inputs to the speech detokenizer to recover the final output speech waveforms. The overall training paradigm of EMOVA consists of 3 stages. It starts with a visual language pre-alignment stage, which actually focuses on the pre-training of the visual projector. It is followed by the omni-modal text-centric alignment and the omni-modal instruction tuning, just as we have just discussed. We provide the detailed training recipe for any necessary reproduction. To better train our EMOVA models, we collect the open source multi-modal datasets as much as we can, followed by detailed data cleaning and data curation. Finally, for the omni-modal alignment dataset, we collect 7.4 million data pairs, while for the omni-modal instruction tuning dataset, we collect 4.4 million data samples. All the training datasets are available on Hugging Face for downloading. We provide 3 pre-trained configurations for the EMOVA model, including the 3B, 7B, and 72B billion variants, to facilitate different kinds of computation overheads. Our 72 billion EMOVA variants achieve SOTA comparable performance on both vision language and speech language benchmarks. It achieves comparable performance with the commercial models, including Gemini Pro 1.5 and GPT-4o models on popular vision language benchmarks, and it even exists the speech expert model Whisper Lodge on the popular LibreSpeech speech benchmarks. Here we will provide several qualitative examples to demonstrate EMOVA's capabilities to conduct emotional spoken dialogue. EMOVA can generate speech responses not only in a suitable semantic contents, but also in suitable and comfortable speech styles.
Imagine you are a parent who is angry at their teenage daughter for coming home past curfew.
I am absolutely furious with you. Coming home past curfew is completely unacceptable. Do you have any idea how dangerous it is to be out late? This is not a joke. You need to understand the consequences of your actions. I am very disappointed in you.
This is a case with the male speaker and the angry emotion. Besides that, EMOVA is actually can support both the English and Chinese spoken dialogue.
为即将结婚的朋友送上祝福。
祝福你们，愿你们的爱情如同晨曦般温暖，永不熄灭。愿你们的婚姻如同繁花似锦，绚烂夺目。愿你们的生活如同诗篇，甜蜜无比。愿你们的未来充满欢笑与喜悦，永远幸福美满。
This is a case conducting a Chinese spoken dialogue with the female speaker and happy emotion. Overall, EMOVA supports 2 speakers, 3 pitches, and 4 emotions.
Hey, I'm so sad these days.
I am really sorry to hear that you are feeling sad. It's important to take care of yourself during tough times. Let's talk about what's been going on and see if we can find some ways to help you feel better.
And this is the case with the female speaker and sad emotion. EMOVA supports omni-modal spoken dialogue. It can well understand the semantic meanings of the input images and the input user speech queries and generate speech responses consistently with the semantic meanings of the input omni-modal inputs.
Write a poem for this image.
In winter's chill, a sad face drawn, a frown of snow, a somber tone. The world is quiet, still, and cold. A canvas painted by the frost's cold. The eyes, 2 dots. The mouth, a line. A simple face, a symbol of decline. The snowflakes dance, they twirl and play, a fleeting moment, soon to fade away. But in this brief sketch, a story's told of winter's mood, of solitude, of cold. So let this face remind us all, in winter's chill, we find our call to feel the frost, to feel the snow, to find the beauty in its woe.
In this case, EMOVA successfully recognized the negative feelings in this image and recognized the speech instruction quite well about writing a poem for this image. And then the final response is actually just writing a poem, a well-formatted poem in a negative scene. Okay, so that's one case to conduct omni-modal emotional spoken dialogue, and in the right part of this slide we demonstrate another case of omni-modal spoken dialogue, working on fine-grained visual understanding.
Based on the image, what is the growth rate for age over 51?
The growth rate for the age group over 51 is 4.22%.
In this case, the EMOVA model successfully extracts the necessary information from the input images and generates the speech responses consistently representing the necessary information to respond the user query. Another important reason to construct end-to-end multimodal models is to break the modality wall, because as the number of modalities increases, it is more difficult or even impossible to collect data samples which not only covers all the involved data modalities, but also covers all the potential data domains, right? So a more practical solution might be to say, now we still want our training data sets to cover as diverse data domains as possible. But just now we do not require each data sample to cover all the necessary data modalities, right? For example, we can say, okay, so for a data sample, you can have connections to only a combination of the involved data modalities, right? So let's say, this subset of data samples covers this subset of data modalities. The other one just covers another set of data modalities, right? And then by training simultaneously on all of these combinations of data modalities, we can learn different capabilities from different combinations. And then with an end-to-end, only with an end-to-end model, we can. It is only possible for an end-to-end model that we can generalize the modality of one combination to another, right? So in this slide, we show two cases, the web UI understanding and the autonomous driving cases, that actually EMOVA is not, we do not collect any omni-modal instruction tuning data on these two domains, right? So but actually for the vision language data, we do cover these two domains, right? So the final EMOVA model, it learns how to deal with these two, the web UI and auto driving domains from the vision language datasets, while at the same time it learns the general capabilities to respond in an omni-modal spoken dialogue. So by learning simultaneously with these two data sources and trying to learn to combine these two capabilities from these two combinations, the final EMOVA model can respond to these two data domains, these two data queries in a quite reasonable way. Okay, so now let's quickly listen to these two cases.
Could you tell me how to use this website?
To use this website, you would need to follow the instructions provided in the header section. It mentions to open a link, which presumably refers to the link provided in the header. After opening the link, you would then need to upload an image. enter text or record audio, and finally click the chat button. The interface suggests that the website is designed for interactive communication, possibly for language modeling or chatbot development, where users can input text or audio and receive responses.
This is the case for the omni-modal web UI understanding, and now let's listen to auto-driving case.
Based on the image, give reasonable driving suggestions.
Based on the image, reasonable driving suggestions would include: first, maintain a safe distance from the vehicle in front, as the car directly ahead seems to be slowing down or stopping. Second, be cautious of the dog on the sidewalk. It may unexpectedly enter the road, posing a risk to drivers. Third, watch for pedestrians and other vehicles, as there are people visible on the sidewalk and other cars in the distance. Fourth, be prepared for possible changes in traffic flow due to the presence of the dog and pedestrians.
So as we can see, even if EMOVA is not directly trained on omni-modal instruction data collected on these two data domains, EMOVA can still can perform omni-modal responding to these two user cases quite reasonably. So I think we believe that this is a unique emergence ability specifically to the end-to-end omni-modal models. Here we present a timeline for all the omni-modal large language models research works we have noticed recently. So after the release of the GPT-4o model, EMOVA is one of the earliest empirical explorations of constructing open-source omni-modal large language models, and it is followed by a lot of research institutions globally. However, among all these counterparts, EMOVA is the only work which is fully open-sourced. Specifically, we have open-sourced all the training and inference code, all the training and evaluation datasets, and all the pre-trained checkpoints spanning 3B, 7B, and 722 billion variants. Our codebase is well organized in a modular code architecture supporting different variants of vision encoders, vision projectors, and large language models backbone. We hope that our codebase can better foster the development of omni-modal large language models research. For the computational devices, our codebase supports training and inference on both the NVIDIA GPUs and the Ascend NPUs. We have prepared a web interactive demo for you guys to better chat with our EMOVA models. And to help you better understand how to use the web demo, we have prepared a video recording to demonstrate several typical user cases of the web demo. So here I will fully play the video recording, but as long as it is enough for you to understand how to use the web demo, feel free to skip the video recording and scan the QR code here directly to start your chatting with EMOVA.
Imagine you are a parent who is angry at their teenage daughter for coming home past curfew.
I am absolutely furious. You know how many times we've discussed curfew, and yet here you are, coming home late again. This is completely unacceptable behavior. You need to understand the importance of following rules and respecting our family's rules. This kind of behavior will not be tolerated.
I am so sad these days.
I am really sorry you are feeling this way. It's important to reach out for support when you are struggling. Let's talk about what's been going on and see if we can find some ways to help you feel better.
Write a poem for this image.
In winter's chill, a face is drawn, a frown of sorrow deep and worn. The snowflakes dance upon the ground, a canvas painted by the cold's profound. The eyes, two hollows, deep and wide, reflect the sadness that the heart inside does hide. The mouth, a line of discontent, a frown that speaks of troubles yet to come. The snow, a blanket soft and white, conceals the world from view. A sombre sight, this face of sorrow drawn in snow, a symbol of the winter's woe. A moment's pause, a breath of cold, a fleeting glimpse of emotions untold.
Could you tell me how to use this website?
To use this website, you would need to follow the instructions provided in the text box at the top of the page. It mentions to open a link, which presumably refers to the link provided in the chat box. After opening the link, you would then need to enter the text or record audio in the right box and click the chat button. This suggests that the website is designed for interactive communication, possibly for language learning or practice, where users can engage in a conversation with a chatbot or another user.
In conclusion, we present EMOVA in this work, which is a top-tier open-source end-to-end omni-modal large language models. Some important technical designs include the semantic-acoustic disentanglement design of the EMOVA speech tokenizer, omni-modal text entry and joint alignment with 3 interesting observations, and the omni-modal instruction tuning stage empowered by the chain of modality design. There are a lot of appealing future works upon the release of EMOVA. For example, one can work on the customization of pre-trained EMOVA models on a specific downstream tasks to improve the experience of personal omni-modal intelligent assistants. And another appealing direction is to lower down the response latency by introducing, for example, streaming processing and full duplex processing of the speech modality. Also, currently, the EMOVA can only conduct omni-modal spoken dialogue or omni-modal instruction responding in a quick thinking manner. And how to improve the omni-modal reasoning capabilities of EMOVA model is also an open question. Thank you for listening. If you are interested in our works and you want to know more details about EMOVA models, feel free to check our website, our web demo, and our Hugging Face site. Welcome to Start if you find EMOVA useful for your own researches. And feel free to contact us if there are any unsolved questions from you guys. Thank you.